Okay, I'm going to try to do perfect squares in less than 5 minutes, and it's very hard for me. Completing the square. I've already messed up. So completing the square. So for you to perfectly get there, understand what perfect squares are. And perfect squares are something times itself. So x plus 2 times x plus 2. But we write it like this, up top, right up there. And for you to understand this, you have to understand that perfect squares always follow the same pattern. And so I would urge you to memorize this on the top right. A plus b squared, there's a pattern. The first term is squared. The last term is squared. Both of them are always positive. And the middle is always 2 times each term. And when it's a minus b, it's still the same thing. It's the first term is squared, and it's plus. The second thing is squared. Second term is squared, and then it's 2 times a, and this time it's minus b, so it becomes minus 2ab. That's the only thing that changed, plus and minus. Once you understand this pattern, you'll understand how to move backwards. So if I'm given this, how would I move back to that? Well, you can always divide whatever's here by 2. So that's what we're going to study. Now let's look over at an example. We can see that x plus 2, x squared, plus 4, and there's that 4x. Now notice that the 4, we have two things we're looking for here. One, we want to make sure our x squared is 1. In other words, we want to make sure there's only one x over here. And the second thing, when I divide this by 2, this number in front of the x, it appears that it's always this number. And then finally, this is also the square root. It's easy to spot when it's a perfect square. Going down here, sure enough, this is the square of this, and this is the square of that. But notice if I divide this number here, minus 14 by 2, not negative 2, just by 2, I get the second term. And then again, it's important that it's only a plus 1 in front of this x squared, and that we're aiming for x's that only have 1 in front of them. So it looks like if I divide the middle term, I can deduce, in other words, divide the term with an x, I can deduce what this second term is. So that's the second biggest key. So this is memorizing this, and then realizing to go backwards, I would just divide the middle term. Let's look at an example and using one of these. Okay, I'm going to just take this one. Pretend you don't have the plus 4 here, right? You don't have the plus 4, you just have that. And before I get there, I want to show you this important notion. If I have 9 plus 1, it's clearly 11. Or 9 plus 2, rather. It's clearly 11. But notice that I can add 3 to either side, and it's still true. And no matter what I add, even multiply, if I were to multiply the whole thing by 2, it's still going to work. But let's just keep adding something. You know, even if I subtract 4.33, as long as I subtract the exact same thing on the right side now, it will work out. And that's the nature of math. But also notice, this is also true. Well, 9 plus 2 is equal to 11. But on the right side, I could just add 3 and subtract 3. It's really the same thing, because if you notice, this minus 3 is the same as adding 3 on the left. But my point is, I can just add and subtract numbers, and it's clear those will just eliminate. And I can add anything. And this is manipulation. And we want to learn this skill for math, because this will help us complete the square. Now, let's go on to this one. This one clearly comes from, if I divide this by 2, I get this perfect square. But I already know that if I expand this one, yeah, I get x squared plus 4x. But I also get this ugly 4, which is not what I want. So keep in mind that I'm trying to find out the perfect square of this, but the perfect square of this is that. So that can't be the perfect square of that. However, it's close. If I divide it by 2, I can see that it's x plus 2. And indeed, I can see it right there, can't I? Well, maybe there's a way of turning this into that. And it's obvious. I just add 4. So that means I can just add 4 up here to create my perfect square. But I'm not allowed to do that mathematically or in chemistry. If to do that, I have to subtract 4. I haven't changed it. I added 4, and I subtracted 4. But now I can clearly see that's what I'm looking for. That's right down there which means in the world of mathematics, when you have something equals to something, you can substitute it. That means I can get rid of all of this, get rid of all that, and replace it with this. I've just found what my perfect square will be to produce this. X squared plus 4x. That'll work every time. In other words, it looks like I'm always subtracting that extra number that is produced from the actual perfect square from this part. This would produce a plus 4 that I don't want, and so by subtracting that plus 4, I get what I do want, which is this part. Will that work for everything that's without a number? If I do x squared plus 6, x squared plus 6x? Well, I know that if I divide that, and that should be an x, by the way. I know if I divide that 6 by 2, it's 3, so I suspect that this is my perfect square. And sure enough, if I expand it, I get most of what I want. X squared plus 6x, but then there's this pesky 9 that I did not want. So I'm close. I can see that what I want there is right. That's what I want. But I don't have a 9 up here, so I can just do this thing again. Well, I'm going to add a 9 and subtract a 9. I haven't created or destroyed anything. I've just put in this portion right here exactly what this is. And that means I can replace it, as you might have guessed, with this. Great. That will expand exactly into what I want, x squared plus 6x, because it subtracts this. It also puts it in vertex format. I can see now minus 3 comma minus 9 is the vertex, and that's kind of the point of why we're doing this. And I can also solve it when it's equal to something much easier than I can in standard form. So this is a very useful thing. But what happens when there's a number there? What happens when I get, we're going to do a few cases. What happens when there's a minus 7 here? Yeah, you could work with the minus 7. Let's take a 10x. And you could work with it, but I actually find it's a lot easier just to push it aside. It's a lot easier just to forget about it for now. And then just use your methods. What's 10 divided by 2? Well, it's clear to me that the perfect square of this will be x plus 5 squared. And sure enough, when I expand it, I get exactly what I want. X squared plus 10x plus 25. The number I didn't want is the plus 25 because there's no plus 25 up here. However, I'm going to add up here a plus 25 and immediately subtract it. And I can see on the left, I have this, which matches this, which means I can replace it with that because they're all equal. So I can get rid of all this part of it, right? And replace it with this. Now all I have to do is resolve those numbers. This I leave alone. These have to add, so I get minus 32. And you can see that works really well when there's no number in front of the x. Minus 30, I forget what the number is. I could just do this and find out. Yeah, minus 32 is the number. So I would rewrite it this, and that immediately tells me my vertex for this is minus 5 comma minus 32. We'll get into solving it later, but anyway, as well. Now, that's great when there's no thing in front of it, and I do much more deep invested ones. But what about when I'm faced with something where there's a 3 in front of the x squared? Well, it's very similar. First things first, push the number aside. So I'm just going to leave that down there. I'm going to push this number aside. Next thing, I don't want that 3 there. So even if it was a minus, let's just say it was a minus 3x squared. And I'm going to take out that minus 3x squared. And by factoring, I divide both those terms by minus 3. And I get that. Now we can use the same method we just used. And we're just going to keep the 7 on the outskirts. The same method is if I divide minus 8 by 2, I get x minus 2, minus 4 rather, is the perfect square. But it's clear to me that when I expand that, what's the extra number? It's always this number squared. And I'm going to let you in on a secret. You just end up subtracting the number you don't want. But anyway, let's just go do it the long way. This will expand to x squared minus 8x and then plus 16. Now at this point, up above, I must put in an extra bracket, and that's because when I factored out minus 3, it means everything I fiddle with in here is going to be affected by that minus 3. So if I start adding and subtracting, I have to create an extra bracket to include it. So it's clear I want to add a 16. And as I said, the secret is just you end up subtracting a 16. So there's that. It's also clear I can see this is the same as this, right? Which means I can replace it. However, I have a pesky number that's inside this new weird bracket that I have to get rid of. And to do that, I have to, because everything in here was being multiplied by this minus 3, if I want this minus 16 out to join the minus 7, I have to multiply it by that. So that minus 3 times minus 16 becomes plus 48. So that means it leaves the bracket as plus 48, like that. And you can get rid of it now. You can just delete the bracket and the number and everything. But not the 3. The minus 3 is still going to be multiplying what I've left behind, which is this stuff. And just get rid of the mess. And then I just have to resolve this. What's plus 48 minus 7? It's clearly plus 41. And you will discover that if you expand all of this, right? If you expand all this new stuff that I've written, and even though the one's wonky, you will get that. But the nice thing about this is I can now see the vertex is 4, 41. What about when the number is not a nice even number? Well, it's the same method. Put the number aside, divide this 3 by half. You can either work in, your teacher might want you to work in fractions, and the nice thing is I can just put a 3/2 there. Or she might want you to work in decimals. For now, I'll be actually I'll leave in fractions because fractions are easy. So 3/2. So keep that in mind that that's the same as this, 3/2. Which means if I were to expand that, fraction, I'd get x squared. And when you expand this, you'll discover this always expands into plus 3x, which is what you want. But then the last number that we're creating is always going to be the square of that. So you're going to end up with this plus 9/4, which you don't want. So that means up top, I'm in the thing I've separated. I'm going to add a plus 9/4 and then subtract a plus 9/4. And then I can see right there, I have exactly this, which is that. So I can replace it with this. And yeah, I want to make my fractions look a little bit more like fractions and all that stuff and make it look better. And then all I have to do is resolve the numbers. So if I look at 7 to get it over a fraction by 4, I have to multiply top and bottom by 4, which minus 7 becomes minus 28/4. And if I do minus 9 minus 28, it's clear I get minus 37/4. So I could just put this right there. And done. That is the expansion of that. Now I could have worked in fractions or I could have worked in decimals, but notice that we're always subtracting the square. That's not it now. But back here, right when it was this, we're always subtracting the square of that. So you can skip all this plus minus stuff and just come up with the thing you want. Just always remember to subtract the square of it. But you also remember that if you had factored out a number in front, to get it out here, you need to multiply that number out. So there you go. I don't think I'm 5 minutes, but it's much clearer, I think.